So I'd like to introduce Junnan Wang, who is with a postdoc over at the Darden School. And she will be talking to us about leveraging a hidden forest to improve the prediction accuracy of random forest ensembles.
Hello, everybody. I'm Junnan from UVA Darden Business School. This is a joint work with Yao, Gushka Cocaine, Asa Paley, and Willis of Topa. And you can see that we are all from business schools. But this talk is about random forest. You might be wondering what a business school is doing in the machine learning conversation. Well, I'll try to make a convincing case. I want to start with something that bothered me for a while. You train a random forest, you add more trees, the error goes down, then it plateaus. You've all seen this curve. At some point, more trees just stop helping. The line flattens out, and there is a gap between where it settles and where the truth lives. The usual story is averaging took care of the noise between trees, and what's left is the part that the model cannot fix. If you want to close the gap, you need to try a different model, maybe a boosted one or a neural network, something with more capacity. What I want to show you today is that this part of the gap can be reduced. It has structure, and that structure is already sitting inside your trained forest. You've already paid for it. You're just not using it. We don't need a bigger model, and we don't need to retrain anything. We just need to ask a different question of the forest we already have. So the structure comes from how a random forest gets built. You've probably all seen this before. The big blue ellipse is the training set, and from it you draw bootstrap samples, about like 2/3 of the training set with replacement. Each sample becomes one tree. I'm only drawing 3 trees here to illustrate. In real life, of course, you have like 100,000 trees. The thing I want you to notice is the overlap. The orange, green, and purple ellipses sit on top of each other. Each tree saw a different sample, but all of the samples came from the same underlying data. The hatched part in the middle is the data that's pretty much the same for every tree. And that's the shared part. When the forest is wrong about something in there because a real pattern is missing or a useful feature isn't in the data, every tree is wrong about it in the same way. Here's an analogy I find helpful. Same picture as before, but I've relabeled the training set to information set and swapped the trees for people. This is exactly the world Paley and So described in their 2019 management science paper. They studied a panel of forecasters, human forecasters, whose information overlaps. They read many of the same newspapers. They probably talk to some of the same people. At some point, adding more forecasters to the panel simply stops helping. And this also traces back actually to Clement Winkler's 1985 insight. In their paper, they said that because experts draw on shared information, their forecast errors are correlated. Those errors are not identical, but also they are not independent. So that correlation creates the ceiling. In their paper, they actually said that with correlation of 0.8, which they found very common in football and economic forecasts, an infinite number of experts is worth only 1.25 independent ones. So that's the ceiling. Their question, and now ours, is can we break it? Their move was clever. This is what you normally ask. Each forecaster's estimate of some quantity X, that's F1, 2, and 3. But it also asked a second question. What do you think the others will say about those quantity? That's G1, 2, and 3. Why does this help? Because now we have F minus G. the gap between the forecaster's own prediction and their guess of others is what the forecaster thinks that the rest of the room doesn't know, but I know it. So the discrepancy comes from each forecaster's private signal. And when we aggregate, the shared part gets counted over and over once per forecaster. So pivoting corrects for that shared part by leaning towards the private signal and away from the shared one. So before we just simply average the expert's forecast to get F bar, now we can pivot away from the shared part. The parameter A controls how much we want to pivot. And the direction is set by the discrepancy F minus G. If the average forecast is above the guess of others, we pivot up. If it's below, we pivot down. Either way, we are moving away from the shared information. And a larger A pivots harder, which helps more when shared signal is dominating the average. The result is the shared error gets put out and the crowd gets wiser. This is powerful when you have human forecasters and you can ask questions to like what others think. But the problem with applying to a random forest is obvious. The trees don't answer those kind of questions. You cannot walk up to a tree and say, hey, what do you think the other trees will predict for this point? Or maybe you can. This is the key trick of this talk. So here is a test point, X, sitting in the test set. We push it through tree 2, the second tree, the green tree in the middle, and it lands in a leaf. The center prediction T2 is just the average of the training labels in that leaf. So far, normal random forest stuff. Now here's the move. That tree, that leaf isn't just a number, it's a neighborhood. The leaf is tree 2's opinion about which training points look like X, called that set of training points I2, the training points that ended up in tree 2's leaf for X. And now we take those training points and we send them to other trees. To tree 1 and tree 3, we ask each one, for this neighborhood that tree 2 thinks is similar to X, what do you predict? Each of the other trees gives back an average prediction over those training points in I2, and so we get an average for the first tree and the third tree. We get 2 numbers. And now we average those 2 numbers. That gives you P2. That's tree 2's pure prediction, which says tree 2 thinks these training points look like X. Here is what the rest of the forest predicts for them. That's inform a guess of others built by tree 2 about its peers. And we can do this for every tree. Every tree has its own neighborhood, and every tree has a pure prediction built by sending its neighborhood to the other trees. So now we have those for the first and the third as well. And so now every tree carries 2 numbers, and the center tree prediction T and the pure prediction P. And here's the part that makes this practical. The trees are already built. We are just running training points through them. We are not retraining anything. So look at where we are. On the people side, Paley and So setup, each human expert has a focus F and a guess of others, which is G. And on the forest side, each tree has a focus T and a pure prediction P. And on the people side, the literature already told us that pivoted simple average works better than the standard simple average. So for the forest, we expect to see similar results. Like we want to know that will pivoted random forest perform better than the standard one? The spoiler is yes. But before the results, a quick sanity check on what the method actually involves. And there are 4 steps. Step 1, train the random forest, very standard, nothing changes. Whatever we are doing today, keep doing it. The second step is to compute predictions. This is the only new computation, just running training point through existing trees, no retraining. And step 3 is to pick A by cross-validation. We use tenfold. You can use more folds if you want. On the training set, we scan from -3 to +3 and a stable 0.1 and choose A that minimizes mean square error across the folds. The negative range lets the method unpivots. If it ever helps, we just don't want to force a sign, and step 4 is just to apply it. And if the optimal A picked by the cross validation is near 0, then the formula just collapses back to the standard random forest. The worst case is that the method does nothing in expectation. And here's what we tested: 11 data sets spanning housing, transportation, air quality, etc. 5 forest sizes, 10, 50, 100, up to 500 trees, each repeated with 10 random seeds. That's 550 configurations in total. We use a 80-20 train test split for each seed. And cross-validation for A runs entirely within those 80%, so there's no data leakage, and everything you are about to see is purely out-of-sample performance. So here are the results across all those 11 data sets. The y-axis is the test set improvement. Positive means pivoted forest is the standard forest. Each box is 10 seeds. The lighter the box, the larger the forest. And the first thing I want you to notice is that most boxes sit above 0. That's 11 data sets, 5 forest sizes each. The improvement is consistent, so it's not one lucky data set. The second thing is that, this pattern I really want you to focus on is that the lighter box, meaning the larger the forest, generally sit higher than the darker ones. So the more trees you have, the bigger the gain. And that's exactly what we would expect, because more trees means more shared signal and more for the pivot to work with. And now I want to walk you through a few of these individually, because the data sets behave differently and the differences are informative. First, bike sharing on the left. This one shows really clean effect. The gain grows monotonically with forest size, and 500 trees is substantial. This is a data set with strong temporal structure that individual trees just pick up in correlated ways, and the pivot pulls that correlation apart. Also for PM 2.5, same story, maybe even cleaner, because air quality measurements have a lot of shared seasonality and weather signal that every tree in the forest grabs onto. So pivoting is exactly the right tool for that. And now look at the all the way to the right, the superconductivity. Almost no change. The boxes sit right at about 0. And I want to be clear, it's not a failure. This is a method working correctly, actually. Cross-validation, look at this data set, didn't find shared signal worth pivoting away from, selected A near 0, and stayed out of the way. So the worst case isn't that this method hurts you. The worst case is the worst case is the method doesn't do anything. And one more thing worth pointing out is that look at the data set on the left again. On the left side of the chart, the improvement, those especially the first two, haven't plateaued with forest size. they are still climbing at 500 trees. So which suggests if we went to say 1,000, 2,000 trees, there will be even more to extract. We haven't hit the ceiling of this technique. And let me come back to where we started. Same data set, California housing. This time I'm showing you 10 seeds at each forest size instead of 10 and also I switched from absolute error to squared error. But the story is identical. The blue line comes down fast, then flattens. And this is a wall right where we left it in the opening slide. And if all you have is this blue curve, the standard random forest, you say that, okay, this forest has already converged. That's as good as it gets, and we should stop there. And now look at the orange line, the pivoted forest. The blue line hasn't moved, same tree, same training, same everything, but the orange line sits below it. Even at 10 trees, there is already a very small gap. And as the forest grows, watch that gap. At 50, it gets bigger. And at 100, bigger still. And 200, 500, the orange keeps going down. The wall for the pivoted forest isn't where it was for the standard forest. It's lower, and still we haven't hit it yet. So here is where I want to leave you. So these are the same trees. We didn't retrain anything. We didn't add new data. We just asked a different question of the forest we already had, and then the wall moved down. So that's it. That's the simple trick I want to share today. Thank you. Happy to take questions.
Awesome. Thank you. We've got time for questions. Sweet. I guess I'm curious, if you wanted to go 1,000, 2,000, is this mostly just a computational problem running forest that big right now?
Yeah. There will be computation costs. Of course, there's no free lunch, but you don't need extra data or training. So why not?
Yeah. All right. Any other questions from the audience? One in the back. Let me run up there.
Is there a repo or an article where we can see more process?
Is there a repo or article where people can go look into this further?
Not yet. We are still working on it. We'll post it there for sure. Maybe you can leave me your email and I can update you when we post it online. Yeah.
Cool. Any other questions? All right. Sounds good. Thank you again.
Thank you.